today's lecture, we're going to start into Chapter 11. Now, both Chapter 11 and 12, the last two chapters in your textbook, are on the topic of comparative cognition. So where we're looking at cognition in other species, sometimes comparing it to humans, sometimes comparing between species, but that's where the comparative side of that is coming. Now, I may have mentioned this a couple of times throughout the course, but comparative cognition is actually the field that I have done researching. So a lot of the studies that we're going to be talking about during chapters 11 and 12 are things that I've either heard about or heard people speak about at conferences, or things that have been relevant to my own research. So I find this topic really, really fascinating, and I hope that you guys can appreciate the topic as well. It's a pretty interesting one. In fact, I'm actually virtually attending a comparative cognition conference this week, so it's kind of perfect timing for me. So maybe some of that excitement will carry over into the lectures this week and next. But Chapter 11 is specifically focusing on the aspects of comparative cognition that relate to memory, and specifically the mechanisms involved in memory. So as per usual, let's start off with some definitions just so that we know where we're starting from. So I've kind of already talked about comparative cognition a little bit in terms of wanting to compare abilities between species. If we want to focus on the cognition side of things, the word cognition is actually Latin for knowledge or thinking, and it's commonly used to refer to thought processes. But by this point in time, you might have realized that there tends to be a little bit of a squabble over specific words and how we use them and what they technically mean, because we can't necessarily talk about cognition in research, especially in comparative cognition, the same way that we might refer to cognition and thinking in our sort of everyday speech. Because typically when we talk about thinking about things, we might say that it's a voluntary, deliberate, or conscious reflection. Sometimes people's definitions of thinking involve some kind of internalized language or sort of reasoning over something. But when we're looking at comparative cognition, when we're looking at non-human animal species, we have a very, very hard time basically backing up anything that goes that deep. So when we're talking about cognition, we're mostly going to be focusing on what we have on the screen here, which is theoretical constructs and models that can be used to explain aspects of behavior that cannot be readily characterized in terms of simple SR or reflex mechanisms. What that's basically saying is that we kind of refer to cognition as stuff that isn't explained by a simple reaction to stimuli in the environment. So we're inferring that there's more going on there, but there tends to be quite a bit of debate as to what specifically is going on there. So we'll talk a little bit later on about different perspectives and what some people think is happening. Some people in the field view cognition in non-human animals the same way that they view cognition in humans, with sort of these voluntary, deliberate, conscious reflections on items in our environments or internally, and others prefer to go with a less anthropomorphized or humanized approach and think of it as simple responses based on prior knowledge that's being accessed. But as I said, we'll kind of come back to some of the different perspectives on the field. But overall, comparative cognition is a fairly broad and diverse field of study. So some of the areas that fall under this umbrella can be things like perception and attention, learning, memory, spatial navigation, time and counting, learning of perceptual and abstract concepts, problem solving, and tool use. So there are many, many different facets that we can discuss. So the upcoming two chapters are meant more to just give you some exposure to the field, give you an idea of what's out there, but not to give you an exhaustive review of everything that could be studied within this umbrella. So yeah, just so you know, it's very, very broad, and we're going to try and touch on lots of different aspects, but there's too much to cover, especially just in two chapters of this one for another definition, we can look at this idea of parsimony, and this comes from the fact that one of the critical features of comparative cognition is the idea that the simplest possible explanation is usually the best way to explain what we're observing. So parsimony is a principle that states that the simplest explanation that explains the greatest number of observations is preferred to more complex explanations. And this idea brings us into that concept I started touching on, where different people have different perspectives on how we should approach comparative cognition. So when I talk about sort of different groups, it's different subsets of individuals who have researched within comparative cognition who share some common core belief on how it should be approached. So the textbook focuses mainly on cognitive ethologists, and then we can come into sort of more contemporary animal cognition perspectives. But if we start with cognitive ethology, this group focuses on the core idea that animals, specifically meaning non-human animals, are capable of conscious thought and intentionality in the same way that humans are. So when they observe a behavior that cannot be readily characterized in terms of simple SR mechanisms, then they have this assumption that there was a thought process that led to this odd or unpredicted behavior. So as an example, the textbook talks about, say somebody's on their way to work, and they have a nagging feeling that they forgot to lock their front door. So instead of continuing to work, they turn around, go back home, and check that their front door was indeed locked. Now, if we were just looking at SR mechanisms, there was no immediate stimulus in their environment while driving to work that should have precipitated them returning home. Usually, while driving to work, they continue driving to work. It's rare and weird that they would turn around and go back home. So that change in behavior was driven by cognition, by that thought of, what if I forgot to do something? I should go fix that. So we can only explain that change in behavior there through some kind of cognitive process. But if we're looking at, say, an animal model, again, non-human animal, where they do some kind of behavior that we can't think of a simple SR mechanism that would have led to that behavior, if someone has a cognitive ethology perspective, then they would say, oh, well, the animal must have thought this particular type of thought, which led to that particular behavior. Now, that perspective tends to clash quite a bit with this idea of parsimony. And so a lot of people in the field of comparative cognition nowadays tend not to subscribe to that particular perspective. But there are some who still subscribe to it. It's just not necessarily the best because it's actually very hard to test. So if we go to parsimony, having this complex thought process going on internally might not be the most parsimonious explanation. Maybe we can come up with some explanation that involves prior learning and experience, or something else that might be a little bit simpler and less difficult to support. Our second point there being that if we're talking about the explanation for these behaviors being some internal thought process, how do you test that? How do you operationalize that and then experiment to show that that is a viable option? If you think back to ideas of what makes a good theory, one of the critical components of a good theory is that it should be testable. There should be a type of setup that you could design that would disprove that theory. But how would you disprove an unobservable thought process? So that's basically the two major reasons why cognitive ethology is not the most common or popular perspective, but it does still have some foundations in modern animal cognition, so we definitely need to talk about it. What we're going to talk about next are experimental psychologists. And this experimental side of things sort of sprung up in opposition to cognitive ethology because of that idea that objective evidence can't give a demonstration either for the existence or non-existence of consciousness. So if we have no way to test for and potentially disprove the existence of consciousness, they said we shouldn't include it as part of our explanation. We should instead focus on things that we can experimentally test. So if we move on to sort of a more contemporary perspective, modern or contemporary animal cognition tends to be mostly synonymous with contemporary experimental psychology. So for them, their definition of cognition is less focused on the thought processes that are driving behavior and more on that abstract idea of it's the mechanisms and the stuff that's going on that can't be explained directly from SR responses. So most contemporary animal cognition will focus on avoiding anthropomorphism, which is basically projecting our own thoughts, emotions, and intentions onto other species. So humans have this tendency to overemphasize our human experience. And even as an instructor, I tend to do that a lot as well, because sometimes being able to relate to what might be going on inside an animal's head were they human makes it a little bit easier to understand different concepts. But I do try also and preface that as it's just a story meant to give you a clearer idea of what's going on. Instead, if we were someone who, say, subscribe to the idea of that cognitive ethology, then maybe we would think that, yeah, this animal just thinks that doing this behavior is going to lead to this better outcome, so they should push this lever because it leads to good things. Whereas when we're doing proper comparative cognition, when we're doing proper experimental psychology, we would rather frame that as they're going to push that lever and it's going to lead to good things, but the animal is doing it because in the past they've learned that pushing that lever yields a good outcome. So there's learning that's going on there. It's based on experience, and it's a lot less based on what they are actively thinking. So again, just rephrasing it, when we're looking at contemporary experimental psychology, we're trying to test cognition with a particular predicted behavioral outcome, something that is testable, to try and give us a better understanding of the mechanisms that are going on and driving what's happening, other than those, what do we call them, simple SR reflex mechanisms. So we're trying to explain more complex mechanisms that aren't as easily explained, but we're trying to do so without assuming human-like consciousness. We're trying to do it without assuming complex thought. So we're going to use theories and models to give us a bunch of predicted outcomes, and then we can run experiments to see which of those outcomes most closely lines up with our theory that led to our predictions. Now that was quite a bit more waffling than I had originally intended to do, but let's move on and talk about a couple of the potential lines of inquiry in comparative animal cognition, contemporary animal cognition. So we can ask things like, how is information stored? Where are we storing it? How does it get stored there? We can ask about how is it retrieved and used? How can we make use of information that we've stored at a later time? We can ask, how do animals navigate through the world? Probably by asking how they're retrieving and using information that was previously stored. We can ask about how they judge the passage of time, how they can have a sense of timing, how are relevant stimuli grouped and stored into categories. There are many, many other different types of questions, but these are just some to get you thinking into how comparative cognition can be such a broad field. But the point of all of these questions is to kind of get you in that mindset that memory is a very important and very central concept to almost all of these topics here. So if we talk about storing information and retrieving information, well, okay, it's how does information get stored into our memory? How do we retrieve memories? How do we use things that we learned previously in order to navigate our world? So memory is critical and central to a lot of other aspects in comparative cognition. And so that's why this chapter focuses so intensely on memory, but we're going to look at memory through a bunch of different lenses, including things like navigation, just to see how things are stored and how we use the information that's been stored. But first off, we should spend some time talking about what memory is. Our definition of memory is going to be the ability to respond on the basis of information that was acquired earlier. Now, for humans, this is fairly easy to assess. You can talk about what you did previously, things that you learned in the past, and things like that. But with non-human animals, you just can't ask them about what they remember, what they have learned, what they have stored in their memory. So instead, what we have to start using is inference. So we can infer that memory is being used when their current behavior is being influenced by previous experience. Now, that definition and that description sounds very, very similar to learning, which is where we started in this course so many weeks and months, I guess, at this point ago. So how do we differ between the idea of learning and the idea of memory? As a refresher, we had talked about learning as an enduring change in responding to a particular situation as a result of prior experience with that type of situation. And we just said that memory is our ability to respond on the basis of information that was acquired earlier. So very, very similar. But we can differentiate between the two based on which aspect or which part of the stages of information processing they focus on. So you might remember the 3 stages of information processing. So we have stage 1, which is acquisition or encoding. This is the process where we are acquiring new information, where we are starting to store that new information. So how it gets from external stuff and how we can store it in some kind of representation somewhere within our brains. Stage 2 is retention, or the retention interval. This is where we store our information, so this is where things are maintained for a more long-term span. And then we can look at stage 3, which is retrieval. So that's when we bring things back out of storage to use at a later date or time. So with learning, with our focus being on this enduring change in responding to a particular situation as a result of prior experience to that type of situation, learning experiments are going to deal with the kind of information that we're acquiring and maybe how we acquire it. So when we look at most studies of learning, we tend to see variation in the acquisition phase. So most learning experiments will have different kinds of acquisitions, so different kinds of exposure to information, to situations, to see how that changes what you learn. Our storage or retention and retrieval stages, phases 2 and 3, those tend to be held fairly constant. And we should note that in learning studies, the retention phase, how long we can hold on to that information, tends to be fairly long, because those studies want to make sure that you're not just repeating it in your head or holding it in your short-term memory. If we want to study learning, we want to make sure that you have actually stored that information long-term. So our constant retention intervals tend to be fairly long, and we tend to have constant or consistent retrieval setups. So with our studies of learning, we're more focused on messing around and playing with the acquisition phase, and we keep everything else constant so that we can see how different exposures during that acquisition phase change what we are learning. So in contrast, for studies of memory, the acquisition stage tends to be kept fairly consistent. We don't care what is learned or how it's being learned, as long as every group has the same learning exposure at the beginning. What we want to start changing is the storage and the retrieval phases. So acquisition in the memory phase, or in the memory experiments, acquisition is only of interest to the extent that it is relevant to these other stages. So we care about acquisition because we can't study retention and retrieval unless we have acquired some kind of knowledge. But what we want to play with, what we want to manipulate in these experiments is our retention phase. So we could have short or long retention phases. So how long do we wait before testing how much you can remember? And we can manipulate our retrieval phases. So what conditions are you being asked to remember things? So we tend to vary our retention and retrieval phases when we're studying memory, and we tend to only vary our acquisition phases when we're studying learning. Now, this isn't true of absolutely every single learning and memory study. This just tends to be the overall pattern that you see when you look at these kinds of studies in general. And this sort of way of framing can help us split apart what the difference is between learning and memory, especially as it relates to something like comparative cognition. Now, in order to talk about memory, we should also talk about the different types of memory. So this should be a little bit of a refresher from something you would have learned back in 104 and possibly in other courses as well. But just very quickly, we can talk about our working memory, which is a shorter term memory. And specifically, if we're differentiating between short-term and working memory, because some people like to make that difference. Specifically, when we're referring to working memory, we're talking about information that's being held just long enough to complete the task at hand. So if you're doing something like mental math or following directions, your working memory is actively working with those pieces of information, with the numbers that you need to manipulate, or with the directions that you need to interpret and follow. So working memory is a very short span of memory, and you only keep that information in your memory as long as you need it to do what you're trying to do. So while you're working, you hold it in your working memory. Our other type that we care about for today's discussion is reference memory. This is our long-term memory. So this is memory of background information that might be needed to use incoming and recently acquired information. So we're using this information that we have stored away, our previous experience, that we can reference against new information that's just recently incoming. So if we use our example of following directions, our working memory might hold our immediate steps that we need to follow, where our reference memory might include our background knowledge of the neighborhood that we're following those directions through. So if our working memory is telling us that the next step is to turn left at this particular street, our reference memory might be that, oh, that street should be coming up soon. It looks kind of like this. And we can break down our reference memory, that longer term memory, into two broad categories. We can have procedural and declarative memory. Procedural memory is our memory for well-learned tasks and skills, things that we can do. So it is a procedure that we can follow. That's how I remember procedural memory. Declarative memory, in contrast, is our memory about the world. Instead of being something that we can do, declarative memory is something that we can talk about. And we can break our declarative memory into semantic and episodic memory. So semantic memory is a store of information that's necessary for functioning within our culture, which is going to basically be our memory of general information. Episodic memory, again in contrast, is memory for particular episodes or things that we have experienced. So episodic memory is our experiences, what we've done, where we did it, and when it happened as it relates to ourselves. So semantic memory doesn't have that personal encoding part of it. Semantic memory is just general facts and figures, but episodic memory is stuff that we have personally experienced. So to help look at this difference between working and reference memory, we're going to look at an older study done by Hunter back in 1913, where they were studying memory in animals. And the specific subjects they were using were rats, dogs, and raccoons. And the idea was to be able to compare this against, say, human children to see how each of these different species could handle very similar apparatuses and procedures. So this memory testing apparatus was actually fairly straightforward. They had a starting box, a position in which the organism would sit. So either the rat, the dog, or the raccoon would sit in this box. And there would be three training boxes or three potential sites where food could be found. And above each of these three boxes, there would be a light. And so one of the three lights would light up, and the light would indicate which box has food in it. And so while the animal is sitting in the start box, one of the lights would come on, and it would tell them which box they should search in order to get food. And what we would do is, so tell them which box has food, turn the light off, and then detain the animal in this start box for variable amounts of time. See how long they can remember which light it was that came on. Then, after that retention interval had passed, they would allow the animal to choose a box. And so if they chose the correct box, then they would receive a food reward. And Hunter was trying to figure out how long of a delay, how long of a retention interval each species could tolerate before they no longer remembered which box they should search. And here, our operational definition of remembering would be finding the correct box at better than chance odds. So at chance levels, there are 3 boxes to search, so you'd probably get the right one about 1 in 3 times, so a 33% success rate. But if you're shown which box is the correct one, you might be able to remember which one is the correct one and get the correct answer more often than would be predicted by chance. So if we see higher than chance levels, we interpret that as remembering which box is correct. As you might expect, the longer the delay, the lower the accuracy across all of the species. But there were differences between species as well. For the rats, the maximum delay that they could tolerate was only 10 seconds. If that interval was longer than 10 seconds, they tended to forget and perform at chance levels. For the raccoons, the maximum delay was 25 seconds. They could tolerate a longer retention interval before they dropped below chance levels. And then the dogs did the best of the 3 species, and the maximum delay that they could tolerate was in the range of 5 minutes, some more, some a little bit less. But they did fairly well overall. Now, we could take this result at face value and say that, oh, rats and raccoons just don't have as good of a memory as dogs, but Hunter wanted to make sure that it was actually memory that they were using to know what the right answer was, because when they started breaking it down, they found that rats and dogs were actually only able to make a successful response when they maintained their body orientation. So what this means is that the rats and dogs would move their body so that they were pointing towards the box that would have food in it. And so as long as they were able to sit still and face the correct box, when their timing interval was up, they would walk towards the thing that they were pointing at, and then they would get their reinforcer. However, if we interfered, if the researchers went in and moved the animal, if they were forced to change their body position, then they dropped to chance levels a lot more quickly. The really cool part is that both raccoons and human children were able to respond correctly, for the raccoons, still with only about a 25-second interval, but still, even if they were distracted and moved so that they weren't able to maintain that body orientation. So there was something about how raccoons and children are encoding that information or storing that information that's independent of their body orientation. Whereas these two species used a strategy that involved body orientation rather than some kind of internalization. And this was vaguely interpreted as some kind of internalization of the external stimuli in such a way that didn't require their body to be facing in a particular direction. All right, the next topic we want to talk about is a paradigm that is often used to study memory. And this is the delayed matching to sample paradigm. So you'll sometimes see it shortened to DMTS. I always just use delayed matching to sample because for whatever reason that acronym just doesn't stick for me. But in the standard delayed matching to sample setup, you have a starting point, so you pick the center key to start. This part of the experiment is honestly just here to make sure that the organism is paying attention. So with our black-capped chickadees, we start with the bird has to fly to the request perch and indicate that they are sitting close to the speaker and ready to hear a sound. This would be key pecking is pigeons, so the pigeon has to peck the key to indicate that they are close to the screen or the array of keys that could light up, and that they are ready to see and are facing in the correct direction, so they could be shown a stimulus. So this is just indicating that you're ready for a trial to start. Then we get into the real process where a sample would be displayed on the middle key. So we have our 3 keys here. You usually start pecking the middle one just because it's central. Then it would light up with a particular type of stimulus. So here they're using different colored lines, different orientation of lines. So they have a bunch of horizontal lines that show up in the middle. On either side, we have 2 keys that start out as blank, but when you're being trained or when you're being tested, we would have those show other options or other orientations of lines for you to choose from. So in early training, you would have the sample that we're matching to would stay visible, just to help them make that connection of what they should be doing and knowing that they should remember what that was. So here they would be given vertical lines on one side and horizontal lines on the other, and the task is to pick which one of these matches our original sample. So if the pigeon pecks the horizontal lines that match the horizontal lines that were presented initially, then they get a food reinforcer. If they peck the vertical lines, then they do not. Once the pigeons have learned that task, that they should be matching what the original sample was, that's when we can introduce the delayed part. Step 3 here is just matching to sample. Once we introduce the delay, what happens is we display our sample on the middle key, and then that sample goes away. And we can have a delay between when that sample disappears and when our options are presented to test how long an organism can retain a representation of what that sample looked like. So later in that training, they would be given those horizontal and vertical lines, but there's no sample directly available to compare it to. And we can manipulate how long they've had to wait to see these options. And again, if they peck the horizontal lines that match the original sample, they'd be given reinforcement. And if they peck the vertical, then they wouldn't. Now, this paradigm is fairly easy to set up, and it's really great for manipulating that delay, that retention period between when you see the sample and when you have to act on the information that that sample gave you. And in fact, something similar to this basic setup has been used with rats, monkeys, chimpanzees, dolphins, sea lions, harbor seals, goldfish, and more. So there's research in many, many different species that show that most animals can do this task. So now that we have the basics of it, let's look at a specific example in one of the coolest species that I have ever seen this done in, and that's honeybees. So This is a fairly recent study done in 2009 by Gross and colleagues. And so there is a video from a similar kind of research by Zhang and al., which would actually probably be the same lab, just somebody else is the primary author. I'm going to see if I can find a convenient way to link that. Right now, the only way I've found is to link the paper, and then you can look at the supplemental materials. I'm going to see if I can find a more straightforward method. But yeah, you might just have to peruse some supplemental material to look at this study. But it's honeybees showing delayed matching to sample, so it's kind of worth a little bit of work because it is just that darn cool. But the way that it works is that at the beginning, we have a tube or a tunnel that the bee has to fly through. And at the beginning, this S is our sample. And so what this looks like is a square card that has some symbols on it. And the dot in the middle is a hole that the bee has to fly through or climb through in order to progress down this tunnel. And so the tunnel is 1 meter long, which means that there is a certain amount of time that will pass while the bee flies down this tunnel. So the amount of time that passes is our retention interval. So during that time, they have to remember what they saw at the beginning as our sample. And then as they go down there, they're going to hit a couple of different rooms. So these are the choice chamber and then the 2 reward chambers, or the potential reward chambers. And they also include what are called baffles. These are basically just like curtains that block the bee from seeing into those chambers so that they can't just see or immediately smell or anything, whatever their reinforcer would be. So they come into this chamber, they have to climb around that baffle. They've passed through the sample, there's no way to look back and see what that sample was. And when they're here, they're presented with 2 possible choices. So they have this presentation and arrangement of symbols or this arrangement of symbols. And they have to choose the one that matches what they were originally shown with the sample. So after the delay of flying down this tunnel, they have to match to the sample that they saw earlier. And so the correct response would be to fly to the left into C1, our choice 1, where they should find a reward. And most research with bees, a reward would be food, probably just sugar water. If they go to the right, if they go to the one that doesn't match the sample, they would then be given nothing. So they should learn that if they match the original sample, they get food. So these are the figures from this study. It's kind of a weird way of presenting it, but what they're showing us here is choice frequency. So how often are they picking that option? At the bottom, we're given our sample pattern, the thing that's shown at the beginning of our tunnel here. And then at the top, we're given what they have available to choose from. So if the sample was these 3 dots, they could choose between 3 dots or 2 dots. And more often than not, they ended up choosing the 3 dots where the choice matched the sample. And they chose the 2 dots where it didn't match less often. And they double-checked that it wasn't just that they had a preference for a particular type of arrangement of dots. They did it with, okay, what if the 2 dots was the sample, and they had to choose between 2 and 3 dots, and they found the opposite, where when 2 dots was the sample, they chose the 2 dots. And they did it with yellow stars because they wanted to make sure that it wasn't just dots or the color blue. They wanted to test that stars and yellow could also work. And they did a whole bunch of different things. Even if you go along here, now it's that there were dots in a particular arrangement and they're being tested with stars, I think, or maybe some kind of yellow smudges. But the arrangement of the items was what was reinforced, not the actual items themselves, and they still matched the arrangement even when we changed what kind of items they were looking at. So they did a whole bunch of different iterations of this study with these honeybees, and they found that even at a 8-second delay, the participants, the bees, were correct 80% of the time. And again, I just find this so cool because I would not have expected honeybees, of all things, to be capable of something like this, even after many second delays. And we can also, at this point, interpret the fact that delayed matching to sample includes both a working memory and reference memory. So the working memory is holding on to or remembering the sample that they have most recently seen and what they need to match to immediately. But our reference memory actually relies on them remembering how the task works. At the beginning, before you start training these bees, they don't know that finding the same sample or finding the same pattern as the sample will get them food. So they have to, over time, learn how the experiment works. And you can actually do this, a complete aside, you can actually do this where if you do delayed, like anti-matching to sample, so you can tell them that if they go to the thing that doesn't match the sample, they can still learn the task. So we can manipulate how the task works, we can teach them how that task works, and they store that process in their reference memory, but they need their working memory to be functional in order to remember what the sample was, and then they use their reference memory to know how to act accordingly using the information that they have recently acquired when they saw that sample. And so, as I've said, even within bees, they've done many, many different studies using many different types of stimuli, many different kinds of arrangements and interpretations, and they've done this with multiple different species. So there have been tons and tons of studies looking at different aspects of delayed matching to sample. And across all of these studies, there are a number of factors that seem to consistently affect delayed matching to sample performance. So the first of these is the type of stimulus that's being used for the sample. Some stimuli seem to be more effective than others, and that the sort of effectiveness of different sample types can also just depend on which species you're working with. We should always keep in mind limitations of the species we work with. For example, in the conference that I'm attending this week, I learned that dolphins are monochromats, meaning that they don't see in color. So if we were asking them to make a discrimination based on color, they would do very poorly at that. So color would be an ineffective sample or an ineffective factor to focus on because of their restrictions. So there are biological and physiological limitations to what makes an effective stimulus for different species. Ooh, words are hard today. All right, second factor that affects our delayed matching to sample is the duration of the sample. So how long are they exposed to the sample at the beginning? The shorter the duration of exposure, the lower the accuracy later on. So if the animal is given more time where they can sort of look at and study that sample, then they're going to be a little bit more accurate later on than if they had a much shorter exposure. And the third thing, the probably most obvious thing, would be the delay after the sample but before the choice. So how long is the retention interval? Again, the longer the delay, the lower the accuracy when they have to then make a choice later. Oh, and I actually forgot that I had included this diagram. This is looking at our sample duration. So this is number 2. So this is how long they were able to study the sample before they moved on. This was done in pigeons, but it's the same basic idea as what the bees were doing, or as the key pecking that I showed at the very beginning. So they were shown a sample and then had to choose between 2 different choices. So if there are 2 options, our chance levels of correctness would be 50%. If they were just blindly guessing, they would be right about 50% of the time. And so this is our percent correct on this axis, and then along the bottom is our delay, specifically our delay after the sample before they make the choice. So we can look at both of those here. So let's look at the first line. So this group was shown the sample for only 1 second. Their performance was fairly high, 80%, if they were very briefly shown the sample, 1 second of exposure to the sample, and could immediately then choose between the 2 options. As they had to wait longer before they were given that chance to choose, their performance dropped off. For our 14-second exposure group, they were given exposure to that sample for 14 seconds, so their performance started much higher, 100%. They always got the right answer when they could immediately then make a choice. And they also show a drop-off in performance accuracy as they had to wait longer and longer to make their choice, but Having been exposed to the sample for longer meant that they always performed better than the groups that had a shorter exposure period. So we see this really nice, predictable layout where, yes, there is a decrease in performance accuracy as the delay to choice increases. And we also see a decrease in percentage accuracy when we look at how long they were exposed to the sample. So the more exposure, the more accuracy, less exposure is less accuracy. So a nice clean graph showing these last two topics that we just discussed. So that's all been talking about can they do this task? Can they remember? And sort of what affects the accuracy of their memory. But we might also want to ask, how is this happening? So we're going to talk about what's called the trace decay hypothesis of memory. Now, this was proposed back in the 70s by Roberts and Grant. And they basically said that presentation of a stimulus creates a stimulus trace in the brain that automatically fades with time, leading to more memory errors. So they had the idea that the presentation of a stimulus would create a change in the nervous system. Something in how our neurons interact would be sort of changed. And so the initial strength of that trace would be related to some characteristic of the stimulus. So if you're exposed to the stimulus for longer, you would have a stronger trace. If the stimulus was more intense or more biologically relevant, it would create a stronger trace. But no matter where you started, the amount of this trace that you had would decay over time at a consistent rate. So we should see a gradual drop-off in the accuracy of choice as time goes on, simply because this trace, this change in our brains, would decay over time. And so from this hypothesis, they said that forgetting would occur at a consistent, predictable rate, and we could look at that rate of forgetting using something called a forgetting function. So looking at that drop-off in performance accuracy as some way of reflecting the strength of memory that's left. So this experiment was a delayed matching to sample comparing red and green with pigeons. So they'd be presented with a sample of either red or green, and then they'd be asked to choose between red and green later on. And so they had 4 different groups that were trained with different delays between the presentation of the sample and the option to make a choice. And then each of these groups was tested with different delays. So if we just look at this first graph here, we're looking at the percentage correct again, so their accuracy on the y-axis, and the second delay, how long of a delay there was between the presentation of the sample and the option to make a choice on the x-axis. So this group was trained with 0 seconds of delay in their training, so they were shown the sample and immediately allowed to choose between the red and the green key. And so for their accuracy, they were really, really accurate when there was no delay between the sample and their choice, but they showed a pretty standard forgetting curve when they were given a delay of 2 seconds, 4 seconds, 6 seconds, 8, and 10. So this graph on its own would go along with our trace decay hypothesis, because we're seeing a gradual decline in what they can remember over time. However, as we move up to our other types of training, we see that those who were trained with a 2-second delay still had fairly high accuracy at the 2 seconds when they were tested. They did show a drop-off after that, so they were less accurate at 4 and 6 and 8 and 10 seconds of delay, but the 0 and 2 second delay were consistent, unlike up here where we saw the drop-off between 0 and 2. And that pattern continues, where if we look at the group that was trained with a 4-second delay, they had the same level of accuracy with a 0-second delay, a 2-second delay, and a 4-second delay. We didn't see a drop-off in their performance until a 6-second delay. And our 6-second delay training group showed pretty much consistent accuracy all the way across. So this isn't showing us a consistent decay of a trace that is constant no matter your training. This is showing that there is there is an effect, there is a change associated with your training. So it isn't just some physiological decay of a trace in your brain, the training matters as well. So they thought that memory faded automatically as a function of time, but that's not so. The decay rate is a lot more related to the similarity between the conditions of testing and the conditions of training. So it isn't just time, and so our trace decay hypothesis of memory is not the best way to explain what's going on. So we might interpret this as the common finding that memory gets worse with the passage of time might just reflect the fact that participants are not usually trained with longer delay intervals. So if we want to delve just a little bit more into what's going on with delayed matching to sample, we can have the idea that animals might be responding by focusing on choosing the correct thing. They might also base their responding by inhibiting a response to an incorrect thing. So if we think of our bees and they have, say, 3 dots to choose from, and then, 3 dots or 2 dots, and the sample was originally 3 dots. If they're focusing on the correct, then maybe they're remembering, I just saw 3, so I should go to 3. If they're inhibiting the incorrect, they would say, I just saw 3, don't go to 2. Or they might use both, where I just saw 3, which means I should go to 3, and not to 2. So that's how they might be framing. Again, a little bit anthropomorphized because it's really hard to describe these things in other ways. In our discrimination learning procedures, which we've talked about previously, we see that animals tend to use both. So they'll focus on the correct and try and inhibit responding to the incorrect. So if you think back to our discussions on peak shift and the fact that we see sort of our positive responding to our S+, and sort of the don't respond to our S-, and we see a net shift of responding kind of that way. So that's what's going on with peak shift, where both focusing on the correct and inhibiting the incorrect come into play. In contrast, for delayed matching to sample, we tend to see more evidence that they're just focusing on the correct. And we can try and break this down into how do they specifically know which one is correct. We might have a general or matching rule saying that if I see something, I should find the same thing. So no specifics introduced, just a concept of the same. Or they might focus on a specific stimulus-response relationship. So if I see red, I should then go to red. So if the bees are trained with 3 and 2 dots, then they might internalize it, again anthropomorphically, as if 3 dots, then should go to 3 dots. And again, very, very concisely, the research shows that it kind of depends on the size of the stimulus set. So what type of rule they use, whether it's general or specific, will vary if they have to use a large number or small number of stimuli. It's based on what they're exposed to. So if they only have a very small set to remember, so maybe they're only like the bees, we looked at say 6 different stimuli that are interchanged. They might be able to rely on specific rules, like red after red, 3 after 3, whatever. But as the sets get larger, we have to then rely on more general rules, because each trial, each exposure tends to be unique, and so specific rules will be less helpful. You can't rely on red after red and blue after blue if you're then exposed to every color on the spectrum. That is less helpful. So as the sets change, as the stimuli that you're exposed to change, sometimes the rules that you use to make those decisions change as well. And as I'm sure you can imagine, we could spend forever talking about this, but for the sake of time, let's continue on. We're going to move into our next sort of section of memory paradigms, and we're going to talk about spatial memory. So our memory for places. So a lot of this is how do we navigate in our environment? How do we find things in our environment? So what is our spatial memory and how can we study that? So most of what we use to research spatial memory are mazes. And I can't remember if I've said this in this class before, but the psychologist's definition of a maze is not what most people think of as a maze. When you envision a maze, you probably think of, those things on the back of a menu where it's either a square or a circle and there's lots of different paths to choose and dead ends and things like that. In psychology, a maze is typically a lot simpler. We're going to talk about a couple of different kinds of mazes. We're going to talk about the Morris water maze and then a radial arm maze. But a Morris water maze is actually just a giant tub of water. It doesn't have multiple path options. It's just an open area. But what makes this something that needs to be solved is the fact that this tub of water is filled with sort of a cloudy liquid. So it's described as kind of milky, which means that you can't see through it. So it's opaque. So it can be colored. We typically see it as just plain white, and it's white so that there can be a platform hidden just under the surface, but it isn't visible. It isn't locatable through any cues other than spatial cues. So the goal here is to have, I think this would be a mouse. You can also do this with rats, but rodents can swim very well and very much hate to do so. So they are strongly motivated to find a platform so that they can get out of the water and stop swimming. So what you'll do is release the rat or mouse into this maze, into this tub of water, and they'll swim around following different paths until they find this hidden platform. And so at first, it will take them quite a while to do that because they have nothing to base their decisions on. So the first time the rat is put into the maze, maybe they're going to do a bunch of circles. They're going to swim around at random until they stumble across the platform, and then they'll stop on the platform. And so we can see that if we look at our escape latency, which just means how long it takes them to find the platform, and the days of training, at the beginning, it takes them a long time to find the platform. They meander around quite a bit. But the next day, they find it quite a bit faster. So maybe this time, they were like, okay, well, that first strategy took too long. What if I go this way? And then they find their platform. Well, that was much, much faster. Okay, so the next day, maybe instead of going around, maybe they just go straight to the platform. And so the only way that they can find that platform, because they can't see it, they can't rely on anything within the tub to tell them, they have to use spatial cues within this room. And so these kind of cues might be something like, well, the door is on this side of the room, and there's whatever this is up on a shelf. And so it's on the side of the container that is sort of opposite this guy and, halfway away from the door or something like that. So they can use spatial cues to help them find that better and faster each time they do it. And that's why we see that the first time takes them a very long time to escape, and they eventually get to find the platform very, very quickly. So only 5 seconds between being dropped in and locating that platform. And there are tons of ways you can use this test. You can drop them at the same location every time. You can drop them at different locations. You can see what happens when you move the platform. Lots and lots of different ways to study what the rat or mouse is doing in these mazes and what information they're using to do that. All right, our next kind of maze is a radial arm maze, and that's what this guy is here. So if you look at this from the top down, it kind of looks just like a starburst, where there are a certain number of arms. The standard that I've seen for the most part is 8, which is what in the image here. You can see 6 or 4 or 10 or 12. It all depends on what kind of study you're conducting. A 4-arm radial arm maze might also just be called a plus maze, but same difference. They function in the same way. What happens is that you'll take, again, your rat or your mouse, put them in the middle here, and they can go to the end of each of these arms, and you can bait them with different reinforcers. So maybe you put a piece of food, maybe you put a chocolate chip is usually a very good motivator for rats. And the idea is you want to see how many correct responses they make before they make a mistake, something like accidentally repeating and going down the same arm twice, or maybe you want to have them know that every other arm has food, or maybe if the maze is set up in the same room, so if the room is like this and the door is over here and there's a bookcase in this corner and then you have your really lopsided maze, maybe you want them to remember that this specific arm is the only one that has food. Again, there's lots of ways you can manipulate these based on what it is you're trying to study. But we can, again, look at how they find food in their environment, how they remember which arms they've already checked for food, which ones they know tend to be reinforced, lots of different things that you can look at. Now, this specific setup of having arms exposed in the air like this isn't really similar to what they would encounter in a natural environment, but we can make some modifications to this to make it more equivalent to what they would have been exposed to in nature. So you can replenish different arms after certain amounts of time have passed. So what you could do is allow a rat to explore 2 of the 8 arms, and then take them away for a day, bring them back to their home cage, and then bring them back. And after a day, maybe the arms will not have replenished, so you want to see if they remember that those 2 arms have already been cleaned, and so they should go to different arms. Maybe you give a delay of a week and want to see if they check those arms again, knowing that they should be replenished after a larger amount of time. Lots and lots of different options here. And of course, there are different modifications where, again, in addition to number of arms, you can have an elevated radial maze like this, where it's up in the air. You can have it down on the floor. You can modify them for use in different species. So you could do this with hummingbirds. You can do this with fish. You can do this with all sorts of different species, again, depending on what it is you want to look at. And so if we want to look at, in general, how do rats, our most common species to study in mazes, how do they accomplish this task? The consensus in general is that they tend not to use odor cues. If you control for odor cues, it doesn't change their performance. They still perform the same. We can ask, do they use a fixed response pattern? Meaning, is there a set rule of responding that they have where they always check the arms in a particular order or in a particular pattern? And the answer seems to be no. They seem to have some memory of what they have recently done and what they haven't done and where food should be, and they can sort of flexibly adjust their choices. So if they're not using sort of some generic response pattern, and if they're not using odor cues, then what are they using to guide their behavior in these mazes? And most research shows that they're probably using distal cues in the room, things that are on the walls around them, things that are sort of distant from them, rather than local cues, things that they might find directly in the maze. So when I was talking about using the position of the door and other items in the room, those would be distal cues, and that seems to be what they tend to rely on most of the time. And just a quick discussion of a study that looked at how we know this. So this was done back in the 1980s, where they were testing if they were using distal or landmark cues versus close-up cues. And so they had 2 different groups, rich and poor. Rich meaning environmentally rich. There were lots of things on the wall in the room. And poor, they didn't have things outside of the maze that they could use to orient themselves. And we can see that over the number of trials that they were given, and we look at our total number of correct choices. Sorry, this one is actually just total choices. So here, making fewer choices means that they are more accurate. Again, needing to check the axes because nobody uses a consistent label. But what this is saying is that our rich group made fewer choices as they learned the task. So this would be out of 8 arms to choose from. At the beginning, they would try 11 or so arms, so they'd wander around quite a bit and use an inefficient search strategy. But once they learned that the things in the environment were good cues to base their navigation on, they only went into 9 different arms, which usually means that they visit each of the 8 arms once, and then they try to start over again and realize that nothing has been replenished. So this is a very high rate of accuracy. And then if we look at our poor group where they didn't have those environmental stimuli, they did show a little bit of improvement, but not a lot. They were still very inefficiently searching, so they weren't going to just the 8 arms once each. They were going multiple times. They were revisiting arms they had already eaten food from, and it's a lot less inefficient that way. So this gives us evidence that supports the idea that they're using those external cues, things distal from the maze. In this study here, we can actually look at the effect of something else, a delay in how long they had to remember the information that they had about that maze. So I kind of already mentioned that this was one modification you could have for a radial arm maze. And in this case, it's a radial arm maze with 8 arms. And in the first trial, they allowed the rats to enter 4 of the 8 arms. Then they removed the rats for a certain delay period. So they would bring the rats back to their home cage and they would wait for a certain amount of time. So at the bottom here, they have 0.7, 0.25, 0.5, 1, and so on hours. So these would just be delays of a couple of minutes. These are into sort of a couple of hours, up to a full day of waiting. And we're back to looking at percentage correct on this axis, but we see that even up to a 4-hour delay, the rats were still very, very accurate in only going into arms that they had never entered before. So they did very well at remembering where they had been and where they still needed to be, even up to 4 hours of delay. Once they hit sort of 8 hours, 12 hours, and 24 hours, their performance drops off quite a bit, but this is still a lot higher than our chance levels. So if there's 8 arms, then chance responding would be sort of 1 in 8. So this is still quite high accuracy even after a delay. But best performance seen with a delay of 4 hours or less. And if we want to come back to the the conversation about how does this relate to rats in their natural environment, we can look at how their search tactics within a radial arm maze compare to what they would do out in the wild. So in this experiment, we're just sort of looking at a modification where the radial arm maze is now no longer elevated. Now it's on the ground. So the rats don't have to stick to the arms. They can now move freely. So these are some predicted patterns that they might expect rats to follow if they were using these different mechanisms. So A, if the rat is released in the middle, if they wanted to be the most efficient foragers, they would search in a pattern that minimized their travel distance. They would go from the inside to the first arm, and then they would just draw a direct line between each of the arms until they were done. They might also use the arms as a path. So they might treat this maze on the ground the same way that they have to treat it while it's elevated up in the air. They might randomly wander about until they've hit all of the points, or they might use what's called thigmotaxis, which is a tendency to stick to the walls. And what we tend to observe in this situation is actually D. So when there aren't elevated arms, when there aren't walls closing off these arms, the rats tend to stick to the arms of the enclosure in which they are given the maze. So as a natural behavior, rats like to stick where they feel safe, which is up against the walls. So now that we've talked about some of the mechanisms involved, now that we've talked about the ways of testing memory, let's look at the actual mechanisms that might be involved. That's what I'm trying to say here. So we're going to look at what it is that we're remembering and how we're doing that remembering. Now, we've already mentioned our stages of memory, our acquisition or encoding phase, our retention or storage phase, and the retrieval phase. What we remember and how well we remember it is going to depend on all three of these stages. So you need that acquisition and encoding stage where you're getting that information for the first time and bringing it in, because you can't remember something that you don't or that you haven't experienced. Retention and storage is important because you can't use that information if you have no way of getting it. And the retrieval process is also important because you have to get that information back out of storage to use it. So we're going to kind of break down how each of these different factors can influence what we know and how well we know it. So let's start by talking about acquisition and stimulus coding. So our experiences, the things that we are exposed to, get coded in our nervous system for retention and retrieval at a later date. So stimulus coding is us referring to how a stimulus ends up represented in our memory. What format is it going to be stored in? Now, it's kind of important to note that the thing or the method that we use to encode our information, the stimulus coding itself, doesn't necessarily have any resemblance to what we experienced in the real world. So our interpretation or our memory of the first birthday that we can recall doesn't actually have any similarity to the actual event. It's just how we have coded that, how we have stored that, and turned it into something that we can then store. So if you think of it like an audio tape of birdsong, because of course birds, but for my work, I look at a lot of spectrograms. And a spectrogram is basically a graph that has frequency on one axis and time on the other. And so the spectrograph is an interpretation of the sound. And if you sort of play through the sound while looking at that spectrograph, it has the same pattern as the bird song. It's going to give us sort of a different representation of it, but the information is being encoded in different ways. It's not the same as a bird naturally producing that sound in the wild. We've changed the format into either an audio file or a digital representation, that visual where we can see a graph of it. You can also have sort of even deeper look at something like digital coding. So if you have an MP3 of a bird song, that information's all being stored as ones and zeros, which is again just another step removed from an actual bird making an actual song. So this idea of stimulus coding is something that we encounter in so many different aspects of our lives. It's just sort of that converting of information from one form to another. So our memories and experiences are not stored as exact replicas of what actually happened. We're storing them some other way. But how? So we're going to consider just as it relates to what we've talked about so far, so mostly relating to things like spatial navigation, but let's think about how an animal encodes and represents the world that they have to interact with. It is very unlikely that a rat in a radial arm maze has a list of the exact number of arms and their exact orientation within one another, and they've listed which ones they have visited and haven't. While that strategy would probably give them a rather excellent performance on that task, it just isn't a viable option. It isn't something that a rat brain would be set up to do. So maybe they have some kind of mental representation of that arrangement of that sort of location. And so we can call this a cognitive map. A cognitive map does not tell us precisely where things are and their orientation to one another. In fact, when we start talking about cognitive maps, we keep the idea fairly vague because, again, it's almost impossible for us to interpret exactly what a rat's cognitive map would look at. What we're going to do is use it as more of a vague concept, as some kind of encoded navigational cue that guides their spatial navigation. So it's some kind of internalized mental representation of their environment, and we have kind of accepted that we don't exactly know what kind of information is contained in that map, how it's arranged, and how they use it. So we're keeping things, again, fairly vague by necessity because it's something that we can't directly study. In humans, it's a little bit different. If you wanted to study cognitive maps in humans, you could ask somebody to sit there, close their eyes, and imagine their neighborhood. What does that look like to you? And you can get an idea of how each individual sort of encodes their information of a space, but again, not exactly possible for other species. We're also later on going to talk about things like retrospective and prospective coding, which is a memory of where you have been and where you have yet to go, somewhere you're planning to go in the future. But honestly, we're actually getting very, very close on time here for today, so I think we're going to call it here, and we will wrap up the rest of this chapter on Tuesday.